Sir, another thing,
Yes, go ahead.
sir, we are only considering the NP and BGT.
Yeah, yeah.
Sir, what will be about the PNP? I
You
mean
want
the
to
para.
use PNP?
Sir,
Why you want to use PNP?
no, sir, I don't want PNP, but I'm curious about want to know about what will happen if we use PNP in those cases that we have already discussed.
Actually, why it is always NPN? Because in NPN transistor, electrons are the main carriers, right? NPN. N is N type. Emitter is N type. So electrons are the main carriers, and electrons they have much higher mobility. So you get higher speed with NPN transistor. But if you use PNP, the holes are the main carrier, and the holes they move much slower than the electrons. Their mobility is less, right? They move at a slow speed, and who wants a slow something, right? You always want something that moves fast, right? When you want to go to buy a car, right? You want to buy a car that moves faster, right? Not to buy a car that goes slow. So everybody likes speed, so that's why it's always NPN. But we will see later on that there are situations where we will need PNP, right? There are situations where we will need PNP and we'll use them. But for now, it's all NPN.
Thank you, sir. Got it.
Okay, so our today's topic is So that is our differential amplifier that shows the main circuit in these different voltages and different components. So this we can show like this. Since it is taking the difference between the two inputs, so that can be shown like this. So this is our VB1, VB2. So that is our differential input voltage. So VID here, VB1 minus VB2. And since we are considering the signal to be small, so that will be less than 20 millivolt. Right? Less than. So that's the definition of small signal. Yeah. So now here we'll have the voltage, the base 2-meter voltage, VBE1 plus minus, and here we'll have VBE2. So these are the base emitter voltages, and this will have both the AC and DC voltages, or the large signal and the small signal voltages. Large signal means that the voltage VB that forward biases the base emitter junction, that is around 0.7 volt or about 700 millivolt. Right? So that is the large signal part, and the small signal part will come from this VID. Even in common mode operation, when these two are zero, so let's put it. So we discussed in last class, but just to refresh your memory, you might have forgot. So in common mode, we said in last class, right? We started with the common mode operation, that VB1 will be equal to VB2. Right? Both voltages will be same, and then VID will be zero. Right? In that situation, these two voltages are same. Right? In that situation, we'll have the base 2-meter voltage VB1 will be equal to VB2, because we have applied the same voltages, and these two also, shorted, and that will be equal to VB. Right? That is our forward bias voltage, right? Forward bias voltage of base emitter junction. So that is what we get, right, when these two are same. Now we are considering a situation where these two are not exactly same; they differ by a small margin, right? Small voltage, and that is the ID. That is only 20 millivolt, right? So initially their voltage about 700 millivolt, right? Or it can be greater than that. Right? It can be greater than that, or at least 700 to make them forward bias. And now they differ by a small margin, that is less than 20 millivolt. So now in differential mode, so we have what we are considering. We have considered this differential mode also in our last class, but that is considering the signal is large. But now signal we are considering to be small or large. So now these two are different. So VB1 is not equal to VB2, right? So these two are not same. If these two are not same, then the base emitter voltages VB1 will also, this will not be equal to VB2. These two will be different. Is that clear, guys? Any question? Does that make sense?
Yes, sir.
Yeah, the emitter is tied together. This is the common point, right? Emitter terminal is common, but the base terminal, they have different voltages. Their level is not same. So obviously these two are not same, right? So in that situation, if we assume that VB1 is greater than VB2, so the voltage here at this point will be higher than VB, and voltage here VB2 will be lower than VB. So that we express, we also showed this in last class, that VBE1, the base emitter voltage for the transistor one, will be our initial forward bias voltage, and that will go up by half of VID, right? The difference between these two, half of will, right, appear here. It will go up by half of this, and VBE2 will go down. It will decrease from initial value by half of this, right? And why half of this? Why exactly it will change by half of VID?
So because the transistors are identical.
Exactly. Last class we said that these two transistors we assume to be identical. So they have exactly same everything. So they're like the parameter that will, I mean, most, I mean, have the influence here, I mean, the determining factor is the base emitter voltage. If these two are identical, then base to emitter, sorry, the base to emitter resistance. If these two are identical, then base to emitter resistance, yeah, which is known as the R pi for Q1 will be same as the R pi for Q2. Since they have the same resistance, then the voltage will divide equally, right? So that we showed in the last class like this, right? We have the two resistance, we have R pi here, R pi here. So that is our, at this end you have PB1, at this end you have PB2. So these two base terminals, right? And this is our common emitter terminal. And the difference is VID. So what you have half of VID here. This terminal is at higher voltage, so plus and minus. This terminal is at lower voltage, so again VID by 2 plus and minus, right? So that only makes sense, right? And then the overall the difference remains VID, right? Plus and minus. So that is how the voltage will be distributed. If these two are not identical, if they have different R pi, then the voltage distribution will be also different. If this R pi is greater, then you have a higher voltage here and lower voltage here. Okay, so we are doing that can happen in, of course, that will happen, that result will happen in real life, but we are considering ideal situation to just simplify our analysis. So we consider them to be identical. So now you see that when this is we distribute like this. Still we have the difference here, VB1 minus VB2 remains PID by 2, right? Yeah, sorry, PID, not PID by 2. Anyway, so that is the case. So in common mode, what we said in the last class, uh, that was about the voltages, right? And the forward bias voltage will be the VBE for both same forward bias voltage. And then since they will have same forward bias voltage in the common mode, this current I will divide equally. Now let's say we assign these currents here, IE1 here, and then IE2 here, right? In common mode, since they have this same forward bias voltage as VBE, so these two currents will be same, right? IE1 will be equal to IE2. So this current will divide equally, and that will be I by 2. So the two currents will divide equally in the common mode. Now we have a differential, different voltages applied in differential mode. And this voltage here, VB1, is slightly higher than VB2. Now what will happen? This current IE1 will go up slightly than its initial current of ID9, I by 2. And this one will go down because voltage area has decreased, right? VB2 is decreased. So now the new currents will be so now the new currents now under in differential mode IE1 will be, we said that will go up. So we have sorry, we have I by 2 plus del I. We have I by 2 plus del I, and we'll have IE2 I by 2 minus del I. Is that clear, guys?
Yes, sir.
Okay. So you see that we have broken down the voltages and currents, right, in both the DC component, which is the large signal part, and the AC component, which is the small signal part. You see that VB1, the forward bias base emitter voltage. So here you have this part, right? This is our large signal, right? And this part is our small signal. Also for the current, so this will be our large signal part, and this current, that will be our small signal part. So that is how in the transistor we have both the large signal and the small signal. So when we analyze this circuit, right, for the DC current voltages, we assume that we don't have this small signal voltage, right? And we remove that one, we just focus on the DC currents and with the large signal currents and voltages. And when we want to analyze the circuit for the small signals, we remove the DC voltage and currents and just focus on the small signal. But the two different types of signals, they need different approach. Any question, guys?
No, sir.
So today's our focus is on the small signal operation. So what we have to do, we have to set the DC voltages and currents to zero. Right? So set this VC to this EC to zero and this I to zero. Right? So when you set this DC voltage and current to zero, what happens? You will not have this large signal in the circuit, right? So this will go. This large is so the voltage VBE for bus voltage will go, and this is also will go. Okay? And we'll be left with the small signal voltages and currents, right? But you have to remember that these are there in the transistor, but we are just not considering them in our analysis. We are just considering this, but these are also there. These are the bias voltage. This is the bias current, right? This is I by 2 is what's the the current with which the transistor is biased. Like uh, when we discuss about the single stage amplifier, the IC, right, is an important parameter. The IC and VC, we call them the quiescent point, right, the Q point, right. So that IC in this case will depend on this I by 2, right? This I differs equally. So that is what the transistor bias to, right? So in this case, the bias current IC will be alpha I by 2, right? So that will be the bias current. You have to remember this. If you want to determine the gain of the amplifier, right? The transistor, how much gain, right? Or the small signal IC, GMDB, right? And also that determines the gain GMRL. So GM will come in different expressions, and GM is nothing but IC by VT, right? So IC is an important parameter, and what is the IC in this case? That's alpha I by 2, right? And that I is this I. So I determines many different parameters for this amplifier, like GM, the gain, right? So this will be determined by this current, and half of this will be shared by these two. Each one will take half of this, right? Here half of I will flow, and here half of this. This is the Q point for the current, right? And then we have the small signal superimposed on this. So the current will fluctuate around this half of I. So if we have a current here, I by 2, right? So total current will be fluctuating around this, right? And this small part here, that is your del I, right? Plus del I minus del I, right? So that is our quiescent point, right? That sets the I by 2. Any question, guys? So when you set this DC voltage to 0, what happens? This will get connected to ground, right? This will get connected to ground, and since I is 0 here, that means this is open, right? So this is open. Only when the circuit is open, so the current is 0. So if in any part of the circuit the current is 0, we can consider that part to be open for the analysis of the circuit, right? So since we have set the condition current to 0, so we can just make it open circuit, and then we just redraw the circuit. It's not working. Okay, so we redraw that circuit, same circuit. considering only the small signal voltages and currents, and assuming the DC voltage and currents are 0. So we have set the VCC to 0, right? So these are connected to ground. And also we have set I to 0. So this part is open, nothing is connected here. So voltage here is, okay, let's keep it like this, VB1 and VB2. So that is our differential output voltage. That's our differential input voltage VID. So current that is flowing here is IC. Okay, IC1. And what is flowing here is IC2. Now VID, this half will have here VID by 2, plus on this side, minus on this side. And also VID by 2, this one plus on this side, minus on this side. So the total voltage is VID. So we did analyze this circuit in the last class. So just go over quickly with this. So we know that IC is the GMDB, right? So in this case, so GM is VID by 2, so we have IC1 will be GM VID by 2, and IC2 will be, since VB is minus, so we have minus GM VID by 2. So minus is it just shows the direction will be opposite. Right? You cannot have negative. Negative means it's flowing in the opposite direction. So it will be convenient for us if we just change the direction of the current. So let's say that this. So we can show it like this upward. So the magnitude is positive in the positive direction of the current IC1 and IC2, and from this we can easily now determine the voltages VC1 and VC2. Here that we wrote in previous slide, GM is IC by VT, and IC is alpha I by 2. So alpha I by 2 VT. Right? So that is GM. We see that we have this DC current, though we have assumed 0, but Yeah, I mean, in real circuit, it is there both the AC and DC, and the GM is determined by this DC bias current I. Now, the VC1. VC1 is the voltage at this collector 1, and since current is flowing towards that node, so it will be minus. So we have minus IC1 RC1, right? And that will be, we have IC1 is this GMVID by 2. So we have minus GMVID by 2 and RC. Similarly, we will have VC2 since current is flowing away, so it will be positive. Let's write RC2 RC. Oh, there's no one, no? Just RC. So that will be plus, so we have GM VID by 2 RC. So we just have a difference of sign, plus and minus, and the magnitude is same. And then we have the expression for the differential output voltage, which is VC2 minus VC1, and take the difference, so it just add up, and that will be GM VID RC. Okay, and right, that's it. So once you have determined the voltages, then we determine the different the gains and the differential gain. You can write it, the differential gain. So differential gain of the amplifiers, that is output by input. Now output we can take in 3 different ways. One is VC1 input is same for all the cases. So VC1 by VID, so using this first expression here, so that will be minus half GM RC, right? The other one we can take at collector 2 called VC2 by ID, and that is plus half GMRC. And the last one, we take the output differentially, so VOD by VID, and that will be GMRC, right? So that is from the last expression here. So now you see that we have so these two together, we call it differential gain for single ended output, right? We are taking output from the single node, right? Either from collector 1 or collector 2, and this one we are taking the output differentially. So this one, differential gain for differential output. And note that differential output is twice the differential gain is twice the gain of the single-ended output or single-ended gain. Any question, guys?
No, sir.
It's all clear.
So how VC1 and VC2 are in the opposite sign?
Because the current, right? IC1 and IC2, they're flowing in opposite directions. See? Right?
Yes, sir. But didn't we make them in the same direction?
We went through that part. Did you miss that? Of course, that they were in the same direction, but VID2 is negative, so we had minus for IC2, right? IC2 will be GM minus GMVI divided, because this is negative, right? GMVBE. VBE is negative in this case. So you'll have a minus sign. And
Yes,
what
yes,
the
yes.
current will?
Got it.
Yeah. We actually went through that part, only you went to sleep now. Okay. What else? Okay, now let's focus on something interesting here. The current that we are discussing, the flow of current. Now this part is positive, right? So you see that positive current will, I mean, the direction of the current flow. Since this side is positive, so the current will flow in this direction, right? So that will be our IV, right? It's flowing in this direction, and this part is negative. So what will happen? This current will flow like this. It will go like this. So that will be positive direction of the current flow, IV, right? And here IE, right, will flow like this. The IC is flowing like this. So this is IE. And this will here, IC is flowing up. So this goes like this, IC, IE. Right? So basically the current IE is flowing like this, right? We are applying voltage VID, and that is how the current IE is flowing. Right? The same IE. Of course, it has to be same, right? The same branch, right? And that goes, so overall, this is flowing like this, right? Is it clear, guys?
Yes, sir.
Okay, now we'll see another important version of this circuit, an interesting version of this circuit. Okay, we go to the next one. Paper picture. Okay, so differential pair, now we have shown, we have seen in our previous slide, the two transistors. Now what we'll do, we replace these transistors uh, by their T model and see what we learn from there. So that is the T model of the transistor in general, right? And we have this, this is the base. So here you have this voltage VB, VB1. Right? Let's draw the another the T model for the second transistor. That will be your voltage VB2. Now, these are the collector terminals, right? And here we'll have the resistances RC connected. And that goes to ground. We have RC. Also, we have RC here. The two emitters are joined together. Just connect these two. Okay, what else? Okay, so now this is the collector terminal. We are taking the voltage, that is PC1, and another collector terminal will taking the another voltage, that is PC2, right? Then VID we can show here like this. So VB1 and here you have VB2, and then so that is our VID, plus and minus, differential input voltage or differential output voltage VOD, this side plus, this side minus. Now the current IE flow here, right, in this direction, and that will flow all the way, and it will go up here. IE. So that is how basically it is flowing, right, like this, current IE. And here it will be alpha IE. Now this is flowing up. So instead of showing this in this direction, so it will be probably more convenient if you reverse the direction here and show it upward, right? Otherwise, we will have to deal with the minus sign. So then you can write here, this is also alpha I. Right? So the same current flowing here, the current that is flowing here is alpha I, and this flowing this way, alpha I. Now VID, this is total differential input voltage. Half of VID will have here VID by 2 plus minus, and also we'll have half here, right, VID by 2 plus and minus. And this is what we'll call the small signal equivalent circuit of the differential amplifier. Any question, guys? Is it clear?
Sir,
Yes.
the polarity of VID by 2 at the second transistor, will it be
Oh, right. Okay. My mistake. This should be plus. This should be minus here. Okay, that's right. Let's correct it. So that should be minus here. Okay, now you see that's how it looks. We have clear picture, the whole circuit, and now also we can do the same analysis that we did before, right? Now we can write the expression for IE. Last time we wrote the expression for IC, we wrote GMVB. That is from our knowledge of the transistor amplifier, IC, GMVB, and now from our the knowledge of the electrical circuits, right? We can analyze the circuit. So this voltage here, the VID between these two terminals, right? The voltage here, VID. And so what we can write for IED? So VID is actually C, that is voltage VID. The plus here, minus here. VOD is here, plus here, minus. So what we can write for the current IE?
So VID by 2RE.
Exactly. So we can write IE as VID divided by 2RE. Right. And then we can write VC1 as minus alpha IE RC, and that is replacing for IE alpha VID by 2RE RC, and we will write VC2 L2 plus alpha IE RC, so that will be alpha VID by 2RE RC. And then we have VOD is VC2 minus VC1. So take the difference, we have alpha VID by RE and RC. So we get in terms of RE, in the last we got in terms of GM, right? We had here minus half GM, right? And the gain also, we can now express the different gains. VC1 by VID, that will be minus alpha by 2RE RC. The VC2 by VID will be alpha 2RE by RC, and the differential output gain VOD by VID will be alpha by RE RC. Any question, guys? So are these two different, or previous analysis and the present analysis that we have got? Are these two different or are the same?
So there is a relation between GM and RE.
What is that relation? Okay, let's see that what is alpha by RE. What is RE? RE is VT by IE, right? So what we get, alpha IE by VT. What's alpha IE?
Sir, IC.
Right, IC by VT. Right? And IC by VT is here. So alpha by RE is nothing but GM. So what we get here, minus half GMRC. So that is same as what we got in our last analysis, right? So both are same basically. We have half GMRC, GMRC. Is that clear?
Yes, sir.
So now we try to determine another important parameter of this circuit. That's the input resistance. In this case, we call it differential input resistance, right? Because we're looking between the two input terminals. We call it denoted by RID, the differential input resistance. And if the current in here is I, let's call it IB, the base current, right? It is flowing this way. Okay, so how do we define RID? The input differential input resistance is voltage by current. So in this case, the voltage is the differential input voltage, and current is IB, the base current. Now, what is IB? What we can write for IB?
Sir, VID by 2RE.
VID by 2R is IE. No? R is the resistance in the emitter.
Yes, sir. Yes.
IB is IE divided by beta plus 1. Right? Is that correct?
Yes, sir.
So this one, if you replace for IE, the IB, so we'll have beta plus 1 that times VID divided by uh, okay, let me put it that way. That will be more straightforward instead of writing like this. Uh, hmm. So what we write here, VID, we write the expression for VID from, we're using this. VID is IE with the times 2RE. So we have IE, VID is IE times 2RE. And that divided by IB. Right? Now IE by IB is beta plus 1. So this one we have beta plus 1, 2RE. Right? So which we can also express as 2 beta plus 1 RE. Right? And what is beta plus 1 RE?
Sir, R pi.
Right. So the resistance will be 2R pi. So that is our differential input resistance, 2R pi. And which actually makes sense, right? How it makes sense? Okay, if we go back to our previous circuit here, see we have the two transistors here, right? And if you're looking into the transistor terminals, um, If you're looking into the base and emitter of this transistor, between base and emitter, you have resistance R pi. And also you have looking into the base of this transistor, resistance between base and emitter is also here R pi, right? So when you're looking between these two terminals, we have R pi and R pi. So together they will make 2 R pi. So from circuit inspection, it is obvious the differential input resistance will be 2 R pi, and that's what we got from our analysis. Any question, guys?
No, sir.
Okay. So now let's answer to this question. Now, if we have a resistance in the emitter, we have RE and also we have RE. So what will be your differential input resistance RID? In this case, we are right.
So 2 R pi plus 2 RE.
That's it.
RE divided by beta plus 1.
Divided by beta plus 1.
Oh, no, sorry, sir. Into beta plus 1 because base to emitter, we are saying base to emitter.
Now, in this case, looking into the base of each of the transistor, the resistance will be R pi plus, we have this RE. So R pi plus beta plus 1, right, times this RE. Right? So that will be the resistance looking into the base of each of the transistors. So the total resistance will be twice of this. Right? So the total resistance will be 2 times R pi plus beta plus 1 RE. So that will be the total differential input resistance. Any question, guys? Okay. So now let's say that we have incorporated this resistance RE, right? Okay. Give me a problem. Yeah, Okay, now the circuit is modified. Can you see this screen?
Yes, sir.
Yes, sir.
Okay. Now the circuit is modified. You have incorporated one emitter resistance, right, into the emitter of the amplifier transistors. So that we can show like this. We have RE, one RE here, and then we have another RE. We have two REs, and then these two are connected, right? So that's how this will modify, and that will be our VID, the positive on this side, negative on this side. The okay, now make some adjustment. That will be more clear. Okay, now see VID, right? Applied between these two terminals. So half of VID will now this point and the emitter point, right? Not just RE. It will be together total. So you can show this VID by 2 plus here and minus here. Similarly for this side, we have VID by 2 plus here and minus here. So the total resistance, right, where we have this VID by 2. The current I, the will flow also like before, it will continue flow like this. Right? Now what will be the current IE?
So VID divided by 2 into RE plus RE.
Right. So now see we have the current expression for current IE here. So here we just modify by RE plus RE. So that's the total resistance, right? So that will be our new emitter current. Right? The total resistance, the differential input voltage divided by the total resistance in the circuit. That is 2 small RE plus capital R. Now you see that the VC1. Can you see this part here? That I'm writing.
Yes, sir.
Okay, no problem. So VC1 will be minus alpha IE times RC. So minus alpha we replace for IE, and that will be given by VID 2 small RE plus capital RE times RC. So that will be our new VC, right? VC1. Similarly, we can write expressions for VC2 and VOD, right? So only modification that will have in the denominator part, the resistance RD will be replaced by RD plus capital RD. Right? So from that we can easily deduce the gain expression. Each of these small RD will be replaced by now RD plus capital RD. So then in this we can write the expressions for the let's modify this part. Okay, let's erase this one. Okay, so we have here alpha RC divided by 2 RE plus capital R. Similarly, in this case, this is just plus alpha RC divided by 2 RE plus R. And in this case, it will be RC alpha RC divided by RE plus R. Is that clear, guys? We just replaced RE by the total resistance RE plus capital R. So just very straightforward. So alpha is close to 1. So this also we can approximate to minus RC divided by 2 RE plus RE. And this one we can approximate to RC divided by 2 RE plus RE. And this one will be RC is RC divided by small RE plus R. Any question, guys? Okay, so if we look at the last expression here, the differential gain for differential output VOD by VID. So that is we have what we have got is RC divided by small RE plus capital RE. So this very simple expression is the ratio of the two resistors, and that we can express as the resistance in the collector divided by resistance in the emitter. Right? And see that if you remember the gain of the common emitter amplifier with resistance in the emitter circuit. Do you remember what is the gain expression?
So for common emitter,
Common emitter with resistance in the emitter resistance in the emitter.
yes, so something similar to this one.
Yeah, it's the same. What is the resistance in the collector divided of the ratio of the two resistors? Resistance in the collector divided by resistance in the emitter. But it had a minus sign. That's the minus sign. But we don't have minus sign here. It's the resistance. So the same formula applies here as well. For the differential amplifier with resistance in the emitter circuit, the gain is resistance in the collector divided by. If you just remember this formula, this is straight away you can determine the gain. It's very simple, right? And resistance in the emitter is the total resistance. The resistance is small RE, and the resistance is the capital external resistance, right? And the gain for the collector, the terminals, right? VC1 will be negative. It will be just half of this gain, right? And gain at collector 2 will be also half of this, but that will be positive, right? So very easy to determine the gains for the different gain expressions for the differential amplifier. So we see that including the resistance in the emitter, it decreases the gain because we have the denominator increases, right? And increases the input resistance, the same effect that we had for the common emitter amplifier with resistance in the emitter circuit. Any question, guys?
No, sir.
Okay, so then that will be all for today, and remember that we'll take the meet next week at the same time.
So third of December, right, sir? Thursday. Meet.
I didn't check the date. Let's see. December next week, Thursday will be third year, right? So it will be 3rd of December and at 6 p.m.
Thank you, sir.
No problem.